the bulk of people who are going to attend. And yeah, I think that's everyone who's going to attend. We'll just let people in as they arrive. So for those who don't know me, my name's Donald McFarlane. I'm a lead engineer at Apollo, and I've been with Apollo for the best part of 11 years now. So today, I'm just going to share my screen. So today, I was going to talk about the highly exciting subject of finite element analysis and whether I have I think that my original brief was, do I have the right answer? And then I changed the title again to, do I have a safe answer? Because I think that's probably the important point we want to get across. So just a wee bit about Apollo for anyone who doesn't know us. We're a Aberdeen-based, well, Aberdeen, Nottingham and Edinburgh-based consultancy. Been working for about 11 years, and we work across disciplines, so oil and gas, energy, renewables. We've got digital applications, things, and a very strong process section. And the aim of the company is really to get away from doing analysis for analysis' sake. We actually would much prefer to give you solutions. So, and we try and be very light on our project management side. So we try to have the engineers leading the work, understand what we want to achieve, and give practical solutions that are doable in a time. So are we 30-second snapshot about me? So I'm a mechanical engineer by background. I started life at Strathclyde University, and then I had a wee detour to Heriot Watt for a bit, and then end up doing research at Strathclyde, looking into pressure vessels and piping. And this is early 90s, so Ansys was really quite bleeding edge then, and they still hadn't even transitioned to a Windows interface, but it's very old school, classic Ansys coding and scripting. And then that all came to an end. That I managed to, from my sins, end up lecturing as a mechanical engineering at Heriot Watt University. Did that for 4 or 5 years, just general mechanical engineers to the courses. But then being in Aberdeen, I realised that my students were probably getting paid more than me, so I joined the dark side and went to Lloyd's Register, which is really looking at plant appraisal, wellhead equipment and mechanical stuff. Pressure vessels, piping, etc. And then after a wee detour to drill kit for a year or two, I ended up in a company called Prospects for 4 years, but I couldn't find their logo because it doesn't exist anymore. And then for the last 11 years, I've been with Apollo. That's been my home here. So what am I? And I like to think that I'm a practical engineer who uses appropriate tools to get an answer. I just want an answer. I don't want to be thinking about extra difficulties. So that generally that ends up either being MathCAD for hand calcs, Excel, STAD for beam models, Ansys. I might get someone else to do Archiflex for me. But what I'm not, and anyone that knows me will agree with me, is I'm not a finite element analysis. I'm not a person that's going to spend 6 months on a specific project. And so that's me. Now we come to why I thought about doing this talk in the first place. When you look around the internet, what you find is that there's lots and lots of information about finite element analysis, but it seems to fall into one of 4 categories. Half of it is marketing, so it's the big boys, it's Ansys, MSc, SolidWorks, just saying use our software, it's really good. There's quite a lot of case studies, so probably issued by a company like Apollo, and they generally look very pretty, they look very complicated, and to some extent they're just showcasing, they're patting ourselves on the back, they're not there for, you get an idea of what the software can do, but if you're to try and replicate it, you find it very hard because there's probably been some heavy duty thought going into the process. There's quite a lot of YouTube's great for it. You can pretty much learn Ansys off YouTube if you want. And basically, I call it the how to do. I want to do X, Y, Z in a software package, be it Nastran, be it Ansys, be it Inventor, be it PTC Creo. It's all out there, so you can figure out what to do. And then there's quite a lot of training type videos. But sometimes I find that I call them, look at all the complicated things you need to know and understand. And quite often it tends to make things harder than they need to be. And to some extent, I could be cynical and say it's some of the analysts trying to demonstrate why they should be trusted and why lesser mortals aren't allowed to do finite element analysis. But that's not what the reality is today. The reality is today is that FEA is fundamentally really easy to do. If you've got Inventor or SolidWorks, they've got add-ons. You put on some boundary conditions, you hit solve, and it gives you an answer. Quite straightforward. And then you move on to the likes of Ansys and the likes of MSC, Nastran, and PTC. PTC have got a package, I forget what their name is, but there's a whole pile of them out there. There's Strand 7. And they're all quite easy to use now. To the point that the universities are teaching the students how to do it. And it's easy for anyone to do, so you don't need to have a degree to do it. You just need to understand that if I hold something here and apply a load, I get these pretty colours, and the pretty colours mean something. So there's lots of information about how to build a model, how to do the modelling, how to choose an appropriate mesh, how to do this, how to do that. But there's very, very little guidance on how to accept your answer. And it's always a question that comes back to me, can we accept this number? So, and to get I put this little graph here, and it was just what I think is you've got a quality of answer, and the quality of the answer is dependent on what's needed. And if you're experienced, you'll get a good enough answer really quickly, and then it'll take you quite a long time to get a better answer. And if you're just beginning, I should expect it takes you quite a long time. You get a sort of fairly long learning curve, but you'll get there reasonably, and you'll get a decent answer. Now, FEA's got a bad reputation in some quarters for, I call it cynic's corner in this thing, because sometimes if you're old school, you associate FEA with being hard and something you only do if you've got a problem, or something that you've designed something, you've put it into service and you've gone, oh, we're not very sure about this, let's do some FEA to reassure ourselves. The other classic statement is you never get a straight answer for an FEA man, because the FEA will raise more questions than answers. So, if it's raising more questions, it takes more time, so it slows the whole process. So instead of doing a quick FEA to prove the answer, the FEA man comes back. Have you thought about this? Have you thought about that? And everyone looks at you. And that's really when the problems start. So real life FEA now really consists of someone building a model, be it in Inventor, be it in Creo, be it in SolidWorks, and either using the inbuilt package, if they've got the professionals to do an FEA, or maybe passing the step file over to someone who's got one of the mainstream packages as a step file, and then you convert it into a model. And then someone just says, okay, run it through the FEA package and tell us, is it safe to use? And there's your problem. How do we know it's safe to use? I came up with a thought process to think about this. So I thought I'll take one, but I'll take a little problem. That's solvable by hand calculations. And then I'm going to equate it to a little test model, and then compare the FE and the hand calculations. I'm then going to take a few exploratory detours into some background stuff that helps understand why some limits are appropriate and why some limits aren't. And then I'm going to suggest, I'll put my head in the block and I'll suggest some limits that if you're halfway sensible, you can live with, and no one's going to tell you off too much. Some people might disagree with my limits, but hey ho, you've got to put yourself out there. So I'm making a basic assumption in this, in that I'm largely letting the software do its thing. I'm not worried about element choice. I'm a wee bit worried about meshing. I'm not thinking about the solution. All I'm doing is I built a model, brought it into Ansys, solved it. And I'm quite happy doing this because 80% the same. You know, the OEMs have a distinct. They want their software to be usable and right. So the assumption is that they've made a certain amount of due diligence to assume that their basic defaults are right. They're not always right, but good enough. And I think this is a valid assumption because I think that's how most people use these packages now. They don't want to burrow into 16,000 layers of click boxes, and you know, you have to remember to tick box X to do box Y, and that's how. So that's what everyone's going. But the real important thing is you've got to think. You cannot blindly accept the FEA as it is. You have to think. You have to apply some common sense to what you're doing. So we're back to square one. How can we accept the results of an FEA? Even that question is open to interpretation. What's the question? Are we confident that the loads we're using are accurate? You know, if the loads are just a good guess, there's no point in doing a really top-notch FEA. You just want to know, are they there or thereabouts? What design code do we need to assess against? Now, if you're in aerospace and pressure vessels and ships, you'll probably find very good, very detailed guidelines about what you need to do and what you can't do. But if you're in structures and just general mechanics, it's largely left to your own choices. So you have to work out what your limits are. So anyway, so you do your answer, you do your analysis, and you get an answer. That's all you get. So now, if I pull this over and see this, well, apologies if I have some things to come out of that. So here's what here's what I built. Okay. For those of you who don't know Ansys, it's fairly straightforward. You bring your geometry in, you assign some materials, and you put some connections in. So what's my geometry? You put some connections in. So in this case, because I'm just basically I'm doing a bottom bracket of something that drops in. So, and here I've got modeled a bolted solution. So that's a wee bolt, and then we just tied the bolt to this area, and we've got 4 bolts. I'm not going to go into. This is just an experience thing of mine. This seems to be the nicest way. There's many ways you could hold this model. You then get a mesh. This is Ansys's default mesh. If you just click mesh, that's what you get. And then you need to apply some loads. So you can see that I've applied the loads to this surface here. And I've got a few load cases. I've got a straight load, I've got the shear loads. I've got a moment. You can't really see the little circle. And I've got a combined load. So you apply all the loads, you get an answer. So you solve it, and it's the wrong picture. And combines. So you solve it, and get rid of this. Okay. And you get an answer. Now, the question is, do we know? The question I'm asking myself, how do we know it's safe? The first thing you notice is, well, actually, maybe you would think that, we're going to assume it's 355 steel, therefore yield is probably a sensible limit. So we could set that limit to yield. So we've got some areas that are close to yield here, and we've got some obvious fails here, and you can see that I've putting big excessive deformation on, and you can see that as a bending moment comes on, it's trying to bend it and rip it apart. This is all looking quite sensible. You'll notice that how you present the results makes so quite often people, you see these nice blended plots. I don't really like them, because what you get is you get a blended plot, and crucially, this is very subtle, is most software displays an average solution. And if I change that display to unaveraged and then reevaluate it, you can start seeing the picture is not quite so pretty. You see all these step joint, and then if we take the contours and just put it to a bit more of that, you can see that in here, that you can see the elements, and you can see that the stress is jumping radically from element to element. So in my first passes, I'm not so comfortable in this mesh. So we'll throw away this model, and you bring in, and then you put another mesh on, and you get a much nicer, much more complete picture. Okay. And contours, put contour bands on. Again, I've got unaveraged plots now, but this time you look at the mesh, you can see that the bands are crossing the elements quite nicely. There's some glitchiness here, but that's probably livable with. There's some glitchiness here, but that's just down to the way I've held this pin. But you can see that the maximum stress is shot up. It's now 1200 odds. So there's something squarely going on. But again, I might put a limit of 345 on, which is yield. But if you're a structural engineer, you're probably thinking of 0.6 of yield. So maybe your limit would be 207 or something like that. And then basically, then you say, oh, everything that's orange has failed. And you're like, oh dear, this doesn't work. So are we happy or are we not happy? Now, if we go back, we can go and do some hand calculations. You know, it's just a hollow tube with some. It's just a hollow tube with a hole in it tied to a base. You can work out. You can do a sum, and you can work out the bolt load. You can work out how thick the plate needs to be. And the important things to notice is for axial, the AIC codes. I'm using AIC because it's A, it's freely available, and B, it's easier to read cold. They split into axial and moment, okay, and they apply different limits for different things. So at the base of for simple axial, it's just allowable the yield stress times the area of the section divided by a factor of safety. In this case, it's 1.67. That equates to the classic 0.6 yield. Oops, let's go back. And at the hole, it does something slightly different. It says that it takes the yield stress times the net area and divides it by a different safety factor. So actually factor safety of 2 against yield. So what they're saying, it's by talking about yield, it's essentially ultimate. It's essentially thinking about it's probably thinking about bending and plasticity happening. Now I did cheat a wee bit. I tuned the size of the hole so that the size of the hole so that these two numbers came out to be. So, and what we're saying is that if we're to do a hand calculation for a straight axial pole, we can pretty much live with 380 kilonewtons. So if I go here and put on this remote force, let's check I put the right numbers on. Sorry, I've lost a remote force. So there we are. So there we are. I put 380 axial force on, and then we look at the result. Now do it. Make that bigger. So we know that this is a pure axial load, 380 kilonewtons. And then we look at the stresses we've got in the model. And I've been quite careful here. So I should be able to probe it. Hopefully everyone can see this. And you can see that on the back of the in there, you can see it's 216 MPa, which feels about right. And that is just your average stress across the section. But round here where we've got the hole, and that was our next section property, we can see that we're actually got stresses way, way, way higher than yield. And even here, you can see something there, but you can see 266. You know, but again, it's still less than yield. And then you have this zone around the thing. And down at the bottom here, you've got these massive numbers. You know, you're up at 2000 MPa. So you're, no. But, you know, it's one of these ones, if you did the code check, you would just check that if you did this by hand, you'd just say that's fine and move on and not get too worried. So here we've got the classic problem of FE. It's throwing up two areas of like slight concern. Yeah. And you can do the same for a moment. Now, what I did do is I just then went back to my model, and you can see that I've just built a very simple tube, and I've got a straight axial force in there, and then I put the design moments on in two directions. Okay, so one's in plane and one's in the plane of there, and then the other goes the other way. And you can see what's happening. You end up there. So again, these are the limits. So you can see that I'll make the distort the results so you can see what's happening. Oops. What's this one? This is a straight. That's a straight pole. Okay, so you end up with poles goes thin. You have these big stress concentrations in the middle, and then for bending, you bend it one way. You see that there's virtually no stress in the middle, and you get tension and compression here. And again, you've got the stress concentration in and about the center. Okay, 600. Which, if you think about it, your mean stress is somewhere around 200. It's a hole. You're going to get You're going to get stress concentration, and you can do the same back to front. Okay, so clearly the AIC design codes is allowing you to go to much higher numbers than you would immediately assess. Okay, and So I'm going to just skip over this for a time point of view, but you can check that this is what, so I applied a combined load and I end up thinking that my stress utilization was about 80 to 90% by code. And my bolts are 50% loaded and we're okay here. So if I did a hand calc, I would almost have accepted this structure without thought process. Okay, for the given load conditions. So I go back to this one, okay. So go back to the straight pole. Display. Sorry, I'm mucking around with my contour. Get into ISO mode. Right, I've simplified the plot a lot here. Okay, that's 238 is 2/3 of yield. 345 is yield. 690 is twice yield. Okay, and 4,100 is the maximum stress. Okay, so you've always got to be a bit careful because people hide these and then they just say, "Oh, it's a stress concentration. We can live with it." So that's what it looks like, and you can see there's nothing much happening inside, and the pattern's sort of the same inside. I'm making notes. I'm just assuming this is a solid welded lump. I'm not going to go into any details. So what you've got saying is that away from an average stress away from any discontinuity is 215 MPa, and that equates to 2/3 of yield or 0.6. We seem to have a stress concentration here of 3, and it's about 3 times the nominal stress. Looking good. In the corner, we've got very high stresses, but I'm going to show you something in a minute about. This is a classic example of we didn't even think about it in hand calc. So they just worked out, if you do the weld stress, you would just work out the average stress in the weld and live with it. So this falls into the finding categories. But the important thing is to say that for different areas in the model, we're going to apply. So for here, we apply one limit. Around here, we're going to apply another limit, and then around here. So you just need to understand that the limits are dependent on the type of loading and the geometry. So, because I had time, I did an elastoplastic analysis. Okay, so what I did here was you assume that you apply some material properties. Okay, you probably can't see that very much, but it's just a perfect. So basically it ramps up to yield and then it goes in a flat line beyond yield. And we just applied the same loading, and then so you can get. So to insert, I need to insert a stress plot. Okay, so what the important thing to realize is what happens in an elastic analysis is as the time goes up, in this case the bottom is time or load, you can see it behaves linear, behaves linear, behaves linear, and then it starts to bend. Okay, and at this point, somewhere around here, the structure started to fail. Okay. So, so I've got some plots out. What's happened there? Okay, so this is the total strain just before plots, and I've changed the top so that these are, so that's like 10%, 20%. That's 5%, 2%, 1%. And you can see just before yield, so the time equals 538, 530. And then what we're saying, you can just see, so this is a 551, which I estimate to be the point where it's failing, is you can just see that the strains are starting to tick over 5%. I never probed that. So you can see that it just stretches. So but what you can see is that yes, you've got quite a lot of strain here. And if I do that, so we'll just leave that, and then we can go back to here. Now, if you do a similar plot, this is the strain plot just as yield, and you can see that how it's going to fail. It's failing in a manner you'd expect. It's just ripping it out from the holes. But interestingly, the actual complete collapse, you know, the complete plastic hinges formed around this area, not in the region of the corners. So all we've done here is saying that, you know, it stretches, and you can, there's a simple trick, like you just project a couple of straight lines, and where they meet here, 550 kilonewtons, that's pretty much the breaking load. And then you just, to get a design limit, divide it by 1.5 or maybe 1.67. And then if you go back a couple of slides, you remember that the maximum axial loads from ASME was about 580. So I'm just going to take a couple of detours now and punch us a time a wee bit. And that to look at how some other places do it. And the most comprehensive guidelines are actually written by the pressure vessel codes, probably because pressure vessels blow up spectacularly and they're expensive to make. So there's a real interest in making them leaner and safer. So the crucial idea is that the pressure vessel codes define two basic types of stress. They define a primary stress and a secondary stress. Primary is best defined as, you know, if you keep increasing the load, there's only one thing that's going to happen, it's going to blow up. So a primary load would be pressure, so you pump up the pressure, slings break. And a secondary load, what you're saying is something's going to bend. You know, heat's a classic one, or displacements. You know, if you push something, or you rely on the fact that the metal just absorbs the energy and bends a wee bit. And then they also consider peak. Now they apply 3 different loads to them. So the primary stresses, if it's just general membrane, it's S. Now S in this case is 2/3 of yield. Now what you're saying, you're allowed some local membrane stress, which is allowing for some discontinuities, but it's not, it's allowing for shape discontinuities, but not concentrations. And it applies a limit of 1.5S, which in this case would be yield. And again, if you've got global bending, it applies a similar limit, and it's 1.5, so yield. So that equates to what we're looking at. The AIC and the structural codes generally give you about 0.6 or 0.67 of a membrane of axial stress, and they allow the bending to creep up towards yield. Where it gets interesting is in the secondary stresses. It's the pressure vessels allow the secondary stresses to go to twice yield. Okay, so it occurs. So again, it occurs at structural discontinuities, but specifically excludes local stress concentrations. And the limit here is 3 times your allowable stress, or in this case, twice yield. So it's quite a big number. And then for peak stress, it says you have to think harder and consider fatigue. So that's, and you can do this by load factor design or allowable stress design. They give you guidelines for both. And PD 5500 is much the same. Ship rules another area where they do it. But the interesting thing is the meshes are, you can imagine the model's 100, boat's 100 meters long. Your meshes are actually very coarse, you know, so 500. But they define a coarse mesh, they define a fine mesh. And they define a very local mesh for fatigue, and they give you different limits for each. The interesting thing is to see that they have a static and dynamic case. So for static loads only, you like to go to 0.8 of yield, and for dynamic, you can go up towards yield. So and then when you look at fine, if they go down to a finer mesh, they're getting much higher. So it's just to say that we're not being outrageous by considering that elastic analysis above yield is acceptable. The structural codes are vague, to say the least. They assume that everything's based on capacity. So they actually inherently allow for plasticity, and you'll see it because they always define the bending moment in terms of the plastic section modulus. So it's inherent in the codes, and you can see it, and sometimes, and 9 times out of 10, you'll see it as if they define an ultimate limit and then divide it by a factor. But they also have a pile of rules in there just to protect you from yourself, mainly to do with buckling and shape factors, etc. AIC for elastic and for finite element analysis, AIC doesn't say very much, but you sort of get the impression that 5% is an implied limit, and Eurocode explicitly states that 5% is an allowable plastic strain based on a load fact. But you have to remember that that's based on a factored load, and the factored loads are about 1.5. Now there's a quick trick called Neuber, and it allows you to equate elastic results to plastic results, and it's a simple area under the curve trick. Stress times strain's energy, so the energy in the elastic model, which is linear, equates to the energy under a given stress strain curve. And then we can, if you have a little play with that. Like that. Okay, and here's a little program. You can download this free from these guys, Abbott Aerospace Spreadsheets. Because it's American, it's in PSI units, etc., etc. So what you do is you enter in your peak stress, and it works out. So there's your peak stress elastic, and there's your plastic, elastoplastic true stress strain curve, and it gives you the stress you may expect. But crucially, it also tells you what the strain is. Now, if you have a wee play, you can derive some limits that become applicable. If you did a full elastoplastic analysis in Eurocode, you would say 5%, and that equates to a strain of 2,175, which would scare anyone for something so simple. And if we were to say that we're going to apply a 1.67 safety factor and do a working stress design, you might think that 1,300, i.e., you end up with a allowable stress of about 2% plastic strain, which is 1,300. And then you can figure out that 1% is about 900 MPa and 0.5% is sort of 600 or 700. So these are starting to throw up some ideas. Now, for the final, on the back of the plastic elastic thing, this is quite a confusing curve, and what you normally do is if you're doing a well design or hotspot, you do a technique called the hotspots. I'll have to explain what's happening here. This picture here, 11. Yeah. And if we take this model here, display. Okay. What I did here, if I that into our combined plot, we have we've got our stresses increasing along here. So I've taken I drew a little line along here, and I've recorded the stresses on it. And you can see that the further away they are from the intersection, the higher the stresses get. And I've done this for 3 models. I've done this for a coarse model, which is this grey one, which was the very first model. I did it for a better model, and then I did it for a fine mesh model. What you can see is that these two actually, away from the corner, follow a very similar path, and that asks you to find the mesh so the peak stress goes up and up and up and up. And if you're to refine the mesh even more, this stress would just go up and up. And that's the classic definition of stress concentration. But this isn't reality. In reality, it's a 5mm tube, therefore there'll probably be 5mm of weld here. So it's going to be slightly thicker at the bottom, and it's going to be. And so what the ship codes tell you is if this is the toe of your weld, you pick a couple of points here and here, you work out what the stress is, and you literally draw a straight line here. And then you record the value here, and that's your stress at your toe of the weld. And then I did something similar on this section. So, this is probably the real stress at the junction. So, but for these sort of stresses, you're not really too worried about the overall loading. But you will be worried about fatigue. So you can equate it to fatigue. So if you've got 10,000 cycles and it's a D class, which is just a good butt welded joint, you're pretty much allowed 500 MPa. So, they're big old numbers, and then probably the real stress at the junction is somewhere in the region of 800 MPa. But that's very unlikely because and in there in reality, there will always be some form of what's it called? Stress relief. There'll be a little thing. So, apologies, it's been a rattle through, but at the end of the day, I have a set of limits in my head which I use to assess things. Hopefully, just my chat will have explained why I got to them. And then maybe you can think of it as increasing difficulty and increasing thought process. So the first limit you can say that is if the average stress in the model, note the word average, so it's allowing you to be a bit peaky, is less than, say, 230 2/3 yield, you can accept the answer, no thinking required. Local stresses, now you can accept the limit of yield. So you have to think a wee bit more about that. You mean if the whole body was, if everything in the stress, the whole body was purely axial loaded to yield, then that's a fail. But if the loading is driven by bending on the tension and compression surfaces, you can probably accept yield. But what you need to make sure is that the inherent allowance is that the stress can redistribute. So as the outside surface bends, so the spring, there's a spring core. So with a wee bit of thinking, you can accept 3, 4, 5 yields for local stresses. Life gets a bit more complicated around stress concentration. I call them stress concentrations, not the right word. It's probably better off as geometric discontinuities. I think I should change that word. And if I take this simple, I use a limit of twice yield before I get really too worried. But there's a very important caveat on that, because what the twice yield limit assumes, it assumes that on the first application of loading, some bending happens, and then thereon after, the object behaves in a regular fashion. So I put in brackets stress range. Okay, so the best way to think of it is actually if you can show that the stress range of an object is less than twice yield, then chances are it's going to be good for infinite life. So when it comes to these sort of geometric stress concentrations, I have sort of three limits. I have like, again, if it's yield, I'm not going to worry. If it's 500 or 490, which is ultimate or 1.5 times yield, I'm going to have a quick look and say, yeah, it's only a couple of elements deep and there's plenty of metal, plenty of good strong metal around. I'm happy. If it's at 690, I'm going to be thinking a bit harder just to make sure that my assumptions are right. But we're probably okay as long as we can say that we're not doing reversal loading. So, you know, it works in pressure vessels because nearly always the loading goes from zero to a number. But on an object like we're looking at, you might have bending going backwards and forwards. So if your bending goes backwards and forwards and you'd allowed it to go to 690 in either direction, you'd very quickly ratchet the thing to failure. And then for the hot stop, you know, for the hot spots, as I call them, I've got some more limits. And again, I start off at, you know, if I'm up to twice yield in the corner, I'm not going to be too worried. If I'm up to sort of 1% strain, which equates to about 2.5 times yields or 900 odd MPa, I'm okay. Just need to think. But once we get to like the 1200 type numbers, you start going, am I happy? So if we go back to our model, which we've already decided that by hand calcs, because we're good engineers and we did hand calculations. Something here. So yeah, it was good engineers and we do and sorry, I've lost a thing. Reset. Better. So I've lost my train of thought. So we go back to our combined load case. So yeah, okay, we have a look at our mesh. The mesh seems okay. And this mesh is basically a 10mm mesh, but I did switch Ansys to work in non-linear mode just to make it the. So let's look at our combined thing. So we've now got some limits. So 1300. Oops. So just let's refresh this. So just to see. The beauty of FE is you can make any plot look good. So that looks a nice trick is to make the blue go. So looking at that plot, you wouldn't think it's too bad, but actually, oops. I've now just applied what I think are our sensible limits. So away from any discontinuities in an area of average stress, you know, and I put hit result, we can probe the numbers. 120, you know, not worried at all. Round the hole, it's still okay. We've got 300 there, 345 there, but there's lots of metal around it, so we're at a yield limit, so I think we can accept that. Down here, you can see it's 290, 500, so we're starting to be into the now, we've already discussed that if I should put the element, that if things are, you know, within 5 millimeters of this code, these numbers we can largely ignore. They're totally totally driven by hotspots. So the just acceptance is, are we happy with 500 odd here? So that's this now becomes, it's just a, I think we can apply our stress range here. So say it's less than 600 MPa. So I think we're good to go, and we can justify that as a high stress hotspot. You need to think about it for fatigue, and I would strongly suggest if this unit was subject to fatigue, it would break, but we're not worried about that in this case. So that is all I was going to say. I could say a lot more. So thank you for listening. I hope I've not bored you too much. That's been a long hour. This is planned to be a series of webinars by Apollo, and it'll be a bit eclectic in what we do. So we're going from, our next one is planned to be a discussion between Nigel and Paul, who are heads of sustainable and carbon energy divisions. And it's just a discussion of the future and how we're going to balance the future needs. So here we are, we're going from something super geeky and detailed into something that's very generic. And that just reflects the breadth of what Apollo does. We don't have a date for it. It'll be probably January or early February. And if you follow us on LinkedIn and all the other media channels, we will let you know. If anyone's got any questions, I'm happy to hang around and answer some questions, but that's me sort of finished. Stop sharing and then. Okay, so I'm open for questions if I haven't bamboozled you too much. If not, we'll say goodbye. Yeah.
Hello.
Hello.
Yeah.
Yes. What's your question?
I am from India. I am piping subsea engineer.
Yeah.
I am working for Technip now.
Okay.
And I have doubt that in a country like India, there is very less scope for subsea and Orcaflex. So I am facing difficulties to do some calculations in Orcaflex because like in Orcaflex, the principles of underwater technology like wave, current plus piping, it is connected to FPSO.
Yes.
So
at Apollo, we do far too much Orcaflex. I'm certainly not an expert, but we've got lots of people.
Can we get any training, sir, for this?
I think we could organise it. I'm not. Drop us a line. We'll see what we can do. The other people that do it are kind of run some they're based in Cumbria in the UK, and they've got quite a nice setup. But it's a bit far for you to travel.
Yeah, so, maybe online training. Maybe I am ready to go for it.
Okay, no, that's fine. Well, I'm sure if you send Roshan, or me an email, we can see what we can organise. We're certainly willing to run training courses. I'll quite happily run an Ansys training course. It gets a bit techy to.
Yeah, thank you very much.
Okay. Anyone else? No. Okay, I think we'll just call it a day there then. Well, thank you for listening to me. I hope I haven't bored you too much. And if you get any queries, just drop me a line. It's donald.mcfarlane@apollo-oe.com. The recording of this will be available on our website or YouTube channel, I will hope, Roshan, and there'll be a copy of the presentation so you can work out what I've done. And if you've got any specific questions, just drop me a line. Okay. Thank you.